Hello, my name is Rui Borges and welcome to this tutorial. So in this tutorial we'll be using the polymorphism-aware phylogenetic models to make inferences of the species tree using allele frequency data. So initially I will give you a little bit of background on the polymorphism-aware phylogenetic models, and once you have this background we will be employing these models to make phylogenetic inferences in red base. We'll be both estimating phylogenies but also parameters of interest. So by the end of this tutorial, hopefully you'll be able to understand why the polymorphism-aware models are different from the standard nucleotide substitution models, what kind of problems do the polymorphism-aware phylogenetic models solve that the standard nucleotide substitution models do not solve, and what more or how more insightful can be the polymorphism-aware phylogenetic models in comparison to the standard ones. So, to start, the polymorphism-aware phylogenetic models, like the standard substitution models, aim at describing the phylogenetic relationships between different species. However, POMOs aim at providing a more complex description of the evolutionary process. And by that I mean that while the standard substitution models aim at describing the substitution process, POMO tries to break the substitution process into its constituent processes and brings a population level description of the sequence evolution. And how does POMO do that? So essentially POMO models the evolution of a population of individuals through time, in which changes in allele content and allele frequency are both possible. But this is best explained by looking at this scheme here. So here I'm representing the typical POMO state space, and as I told you, each state represents a population state or a possible population state. In this case here I have 3 individuals and all of them have the same allele, the red allele or the nucleotide A allele. So this is an homogeneous population state and we call it fixed. But we also have polymorphic states in which some individuals of the population have, in this case, 2 of them a red allele and 1 individual has a blue allele. But the state space composed by fixed and polymorphic states per se, it's not a very complex description of the evolutionary process. The description comes from assigning different processes to these arrows that lead me to change from one state to another. For example, once I have a fixed state and I jump to a state where there's a new allelic variant, I may say this black arrow represents a mutation. Again, when I'm in a polymorphic state and the frequency of a certain allele increases or decreases, it doesn't matter, I may say these gray arrows represent drift events. So depending on the processes that I'm assigning to these arrows, I may have a more or less complex description of the evolutionary process, but still a much more complex description than the standard nucleotide models, because those would model a substitution which would be jumping from this fixed state to this fixed state. And POMO accounts for all the intermediate possibilities and events that a population may actually be in during time. By providing this more complex description, POMOs of course stand out from the standard models of evolution. And there are different reasons for that. The first one is that POMOs permit to disentangle the contribution of the different evolutionary forces to the evolutionary process. For example, POMOs account for explicitly for genetic drift, mutational biases, and selection. Another thing is that because POMOs include polymorphisms in its state space, they permit to perform inferences with data from multiple individuals and populations. Typically, interspecific variation is discarded in the standard models, but in POMOs it is fully accounted. Another thing is that POMOs naturally account for incomplete linear sorting. Incomplete linear sorting, it's the persistence of ancestral polymorphisms through consecutive speciation events. And sometimes it can lead to cluster populations that are not really closely related, and this is a known process of phylogenetic discord. And this is best explained actually with the scheme that I have here. So imagine the evolution of these three populations. We know by the gray relationships, this represents the species tree, that the population 1 is closely related to population 2, and the first population to diverge is population 3. So ideally, we would obtain the relationships for these populations that would join or that would cluster population 1 with population 2. However, if you see the evolution of this polymorphism in specific, so it's an ancient polymorphism, it's always present through the evolution of these three populations, and is present at the different speciation events and or divergence events. And unluckily enough, when population 1 diverges from population 2, the green allele is fixed in this branch, but the red allele is fixed in this branch. So when at the present, so typically we get information in the present, we look at population 1, 2, and 3, we tend to cluster together population 2 and 3, and not population 1 and 2, despite 1 and 2 being closely related. So this is the process of phylogenetic discord that incomplete linear sorting tends to produce, and that POMOs are able to correct for. For example, the standard models are not able to correct for incomplete linear sorting. Finally, an aspect that is related to another process to estimate the species tree, which is the multi-species coalescent. So this is also an alternative to estimate the species tree, and compared to POMO, it is more computationally intensive. And this is because in order to estimate the species tree, the multi-species coalescent has to circumvent the many constraints between the species tree and the genealogical histories, while POMO does that naturally, and therefore it directly estimates the species tree. So overall, POMOs constitute still a full likelihood method, yet very computationally efficient to estimate the species trees. And today we'll learn how to do Bayesian inferences with POMOs.